Alrighty, let's open up to page 176. So yesterday we were looking at x-intercepts a little bit more. Okay, we've been dealing with x-intercepts for a while now. But in this particular section, we're going to start to kind of identify or try to figure out where x-intercepts are located. Like how many do we have on the right side of the x-axis, how many are on the left side, how many are at the origin, how many are imaginary. We're going to get a little bit more specific with those. Okay, and yesterday we specifically looked at the positive side, the negative side. Okay, that was the Descartes rule of signs, like we had to look for those sign changes. And then we finished yesterday with looking at where x-intercepts were at the origin, aka 0. Today we're going to take a look at imaginary x-intercepts because those might be a little bit new for us. And then we're going to tie kind of everything together with some graph examples. Okay, so to kind of kick off this imaginary part, we're going to take a look at a parabola, aka a quadratic. I'm sure you spent a lot of time in Algebra 2 talking about parabolas. Okay, it's kind of like the main study of that course. And then in pre-calc you get into cubics, quartics, quintics like we've been working with. Later this year we're going to take a look at exponential equations. Maybe you've seen those in the science class before. And even log equations. Maybe you've dealt with those before. I think in chemistry sometimes you use those. So we're going to look at those later this year. So take a look at this graph. We know this is quadratic. Okay, it's a parabola. Here's the specific equation, okay, if you want to look at it. But notice how this graph doesn't have any real x-intercepts. Okay, we did not graph any. But if it's a quadratic, how many x-intercepts should it have? Yeah. How can we tell? Yeah. It should have 2. How'd you know? Yeah. The exponent, the degree. Good. Okay, so since it's a quadratic, the degree is 2. That's telling you how many x-intercepts you should have. Clearly, we don't have any graphed. Okay, none of them are real. So what must those 2 x-intercepts be? Yeah, imaginary. Okay, so that's what we're going to try to figure out. What are the imaginary x-intercepts for this graph? They're not plotted, but that doesn't mean they're not there. Okay, we just can't see them. So let's go ahead and check this out. We're going to figure out the value of b squared minus 4ac. Remember, for a quadratic, those a, b's, and c's are kind of the coefficients in front of the x's. Does this look familiar, though? B squared minus 4ac? Do you know where that comes from? Yeah, Tori?
The bottom of the quadratic formula.
It's in the quadratic formula. It's not the bottom, though. You have an idea, Rachel? Not Rachel. Sorry, Rebecca? Mm-hmm.
It's under the radical.
It's under the radical or the square root. Okay, so we're going to take a look at that further today. Do we remember the quadratic formula? I think I sang it for you guys at the beginning of the year. I embarrassed myself once. I'm not doing it again. Yeah?
Is it like negative b?
Uh-huh.
And then plus or minus?
Yep.
And the square root b squared minus 4ac.
Yep.
Divided by a.
Close. Oh, 2a. Good. Okay. There's our quadratic formula using the a, b, and c from a quadratic equation in standard form. And the quadratic formula always gives you the x-intercepts, those zeros. Okay? So what we're going to do is specifically look at this little section, okay, just the b squared minus 4ac part, because if we can analyze this little section, that might be able to tell us if the x-intercepts are real, okay, are they graphable, or are they imaginary. Okay? So let's go ahead and take a look at this one for our example. So if we label what a, b, and c are, the coefficient in front of the x squared term is 1, the coefficient in front of the x term is 2, and the constant term, aka the term without an x in it, is 2 as well. All right, so b squared minus 4ac, we would need 2 squared minus 4 times 1 times 2. Which is 4 minus 8, aka negative 4. All right, so if you could imagine using the quadratic formula, okay, you would end up with a negative 4 underneath that square root. What do you think that's telling you about your x-intercepts? Yeah. How'd you know? You cannot have a negative under the square root. So when it comes time to actually figure out what your x-intercepts are, notice how just this little section of the quadratic formula is predicting or determining whether your x-intercepts are real or imaginary. If it's a positive number under the square root, we know we can calculate those. So they're going to be real x-intercepts. But if they're negative numbers is left underneath the square root, those are going to be imaginary. Okay, so we'll make note of that. We'll say the roots or zeros or x-intercepts, whatever word you want to use, are imaginary because negative 4 would be under the square root. All right, so we know we should have imaginary ones based off the graph. Okay, but again, maybe we didn't have the graph. Let's say we just had the equation. We could determine that we had imaginary ones by figuring out the inside of that square root, b squared minus 4ac. Let's actually use the quadratic formula to see what the roots would look like, okay, what the imaginary numbers would be. So we're going to fill in the rest of this quadratic equation. So we need the opposite of b, which would be negative 2, plus or minus the square root. Inside of that, we've already calculated a negative 4. And on the bottom, we have 2 times a, which would be 2 times 1, or just 2. Okay, we're going to try to simplify this. So we're going to dig deep a little bit from last year when you dealt with imaginary roots or imaginary numbers to kind of help us simplify this part. Can we think about what the square root of negative 4 would look like as an imaginary number? Yeah.
Would it be 2i?
Good. Okay, so the square root of 4 is 2, just like any normal calculation would give you. But since it was negative, we know it should be an imaginary number, so we're going to use the letter I to denote that it's imaginary. All right, and this is all over 2. Now notice how all the numbers are 2 in there, so we could probably simplify everything. If we divided everything by 2, we would have negative 1 plus or minus 1i. Okay, if you want to go ahead and break this up, you can. I forget, did I tell you guys what I refer to this as? If you have one thing in the denominator? Did I go over that with you guys? Now, okay, now you remember we're all adults, right? Okay, so if you have a single term denominator, okay, one thing down in the denominator, you can break up your fraction, okay, doing each division separately. Negative 2 over 2 is negative 1. 2 over 2 is 1. You still have the I there. Okay, so what's going on here? We said there should be 2 imaginary x-intercepts, right? What are the 2? Can we label them? What do you think, Tori? Right, okay, so that plus or minus is giving you 2 imaginary roots. One's going to be the plus version, one's going to be the minus version. Okay, now we cannot graph these, okay, imaginary numbers not graphable, okay, but notice how we still have 2, just like the degree of the quadratic formula told us we should have. Okay, so we can't see them, but this is what they would look like as imaginary numbers. right? So something interesting here. Since imaginary roots come from taking square roots of negatives, okay, in the quadratic formula, what can be said about the possible number of imaginary roots? For instance, can you ever have one imaginary root? Are you always going to have two? Can you have three? Can you have four? What do you think? The number of imaginary roots. If you were to go through this quadratic formula every single time, yeah.
You don't never have two because the plus or minus is already set in the equation, so you're always going to have the plus or minus if it's imaginary.
Exactly. Okay, so you're always going to have two in this case, all right? But if it's a quartic equation, you could have four, okay? You're always going to have some even amount because of that plus or minus in the quadratic equation. So we're going to say imaginary roots always show up in pairs, kind of like a buddy system. You always have an even amount. Okay. So what I mean by a pair is, notice how you have -1 plus I and -1 minus I. Okay, that would be the two pairs. What if we knew one imaginary x-intercept was 2 plus 4i? What would the pair be? What would the other one look like? Yeah. 2 minus 4i. Good. Okay, so they're going to show up in pairs. What if one of them was -3 minus 2i? What would the pair look like? Yeah.
-3 plus 2i.
There you go. So notice how you're only changing the plus or minus between the two numbers. Okay, you're not switching everything. It's not like this is becoming 3 plus 2i. It's just the plus or minus. Okay, so imaginary numbers always show up in pairs. We're going to use that today too. Okay, that concept. All right, so let's go back to this equation from yesterday. This is the one that we kind of practiced the Descartes rule of signs on. How many positive, negative, and zero? What are the possible numbers of imaginary roots for this one? How many roots should we have? Let's start there. How many total ones should exist? Can you tell? Yeah. 4. Okay, so we'll label our total as 4. So if imaginary roots always show up in pairs, what are the possibilities? Can we think about them? Yeah. 2. Okay, so 2, 4, or 0. Right. Okay, maybe you don't have any. Maybe they're all real x-intercepts. So imaginary roots always show up in pairs. All right, so now that we have discussed positive, negative, 0, and imaginary, we're going to try to use kind of an organized chart method to help us list all of the possible roots of an equation. And then we're going to go through the different kind of combinations that could happen and try to determine which combination is the correct one. Okay, which combination of positive x-intercepts, negative x-intercepts, 0, and imaginary is the right one for a particular graph. All right, so I think, let's see. Now that you've gathered all the information, draw a table. Okay, let's go ahead and use this same equation as we did from yesterday because we already know some things about that. All right, let's go ahead and practice our Descartes rule of signs. All right, so we already have the original equation at the top. Let's go ahead and count how many sign changes we have. If you move from one term to the next, how many times do you go from a positive to a negative or a negative to a positive? Good, Maddie? Can you label them for me? All right, so I like this one because you go from a positive term to a negative. But I'm not quite sure about this first one, because notice how this is a positive 2x. You see how there's no like minus sign out front? Okay, so this is a positive term to another positive term. That's not necessarily a sign change. I do like this one though. Okay, did you find another one then? There we go. All right, so we have two sign changes. Okay, so that's the maximum number that we have. But what's another possibility from yesterday? It was in that little paragraph I had you guys read. Yeah.
We could do negative p of x to find the negative root.
Okay, so we're going to get to that in a second. Okay, there's still one other combination here that might exist. Yeah.
It could have 0.
It could have 0. How'd you know?
Because you can have, it can be an amount of sign changes,
Mm-hmm.
or any multiple 2 that's less.
Multiple 2 that's less. So you're going to take your maximum number that you identified based off the sign changes, and you're going to subtract 2, okay, until you kind of run out of options. So if we subtract 2 from 2, we get 0. We can't subtract 2 again because there's no way we can have a negative number of x-intercepts. So 0 is kind of like your ending point. Let's go ahead now and talk about the negative ones. So we're going to have to plug in negative x into this original equation, okay, see what it turns into, and then take a look at those sign changes. Do we remember the little shortcut from yesterday? Like which ones are going to change, which ones are going to stay the same? Yeah? The odd degree ones change. Okay, so notice how this positive x to the third, if we were to plug in a negative x in there, it would become a minus. Same thing for the 2x, because that's technically an x to the first power. It would change to a minus 2x. Okay, so just the odd powers change. How many sign changes can we identify in that negative equation? Good, Marie? 2, okay. Can you label them for me?
The transition from 2x to 4 to negative 2x.
Okay.
To first, and then negative 2x to 3.
All right, so we again have a maximum of 2 negative ones. Okay, so graphically speaking, we could have 2 x-intercepts on the left, but the same reasoning for the positive ones, if you subtract 2, you also might have none over there. Maybe we don't cross the x-axis or touch it at all. Okay, there's another combination. We said before that the possible number of, we'll skip down here, the imaginary roots were 4, 2, and 0. Because the degree is 4, that's an even number, that's a possibility. 2 is also a possibility because that's an even number, and then 0 is another possibility. Maybe you don't have any. What about the number of 0 roots, like at the origin? Go ahead, Tori. How'd you know?
Because there's a constant term at the end, so you have to factor out x.
All right, so we'll say x is not a GCF. Okay, we looked at that yesterday. If you can pull out an x out of every single term, you will cross or touch at the origin, depending on the multiplicity. All right, so out of all of these possibilities, we're going to kind of create an organized chart to list all the different combinations. All right, so in terms of a chart, let's go ahead and I'll show you how I set this up. You can set it up however you want if you have a particular preference, but we're going to make some columns here. Okay, a positive column, negative column, 0 column, and imaginary. And based off of these numbers that we listed as the possible options, we're going to go through all the different combinations of these possibilities. Keep in mind, we said we should always have a total of 4 because that's what the degree was, the highest exponent. All right, so let's just go ahead and start with maybe the positive ones. Let's say we have 2 positive x-intercepts. Then maybe we'll consider the fact that we could have 2 negative x-intercepts. We always know we're not going to have any 0 ones. Okay, that's the only possibility for that type of x-intercept. let's go ahead and think about what the imaginary would be. So if you have 2 positive, 2 negative, none that's 0, and your total has to be 4, what must the imaginary option be here? It's either a 4, a 2, or a 0. Yeah. How'd you know it was 0? It can't be over 4. We already listed 2 here and 2 here. That's a total of 4. All right, so we can't have any there. So that's one combination based off of these numbers. Let's try another one. Maybe we have 2 positive x-intercepts. This time, instead of choosing 2 negative ones, because we did that last time, maybe we'll use the option of 0. We're always going to have 0 roots. So if we have 2 positive, no negative, no 0, how many must be imaginary? Bless you. Yeah, 2. All right. Let's go ahead and try another combination. Maybe we have 0 positive roots. Bless you. Maybe 2 negative ones. We'll always have none at the origin. So what's the possibility for imaginary? Yeah, 2 again. Okay. And maybe the last combination that's possible, we could have 0 positive, 0 negative, none at the origin. So how many imaginary? Yeah, 4. Okay. So what we're doing is we're taking all these different possibilities and writing out the different combinations of all of them put together. I think that's about it that we can take into account. So we can either cross twice on both sides. Maybe we only cross twice on the positive side, which means the other 2 are imaginary. Maybe we cross twice on the negative side, so the other 2 are imaginary. Maybe we don't touch or cross the x-axis at all, okay, on the graph. That means all 4 of them would be imaginary. Okay, so these are all the different possibilities of x-intercepts that this graph or polynomial would have. It's up to us, okay, and we're going to use a calculator to be a little bit more quick with this, to determine which of these combinations is the right one. Okay, these are just telling you the possibilities, but only one of them is going to be true. So what Descartes would have done is he would have tried to graph this by hand, okay, plotted some points, and then he could determine which one it is, but we're a little bit more advanced in this day and age, so we're going to go ahead and we're going to go ahead and graph it, and we're going to see which one's the right one. Okay, so go ahead and turn on your calculator. Where do we go to type in an equation? Remember? Yeah, y equals. If there's anything in there, go ahead and clear it out. And we're going to type in the p of x equation that's kind of in the middle of your page. Alright, before you hit graph, maybe go to window. They don't really give us an idea about which numbers to use, so you can use whatever you want. You can do -5s to +5s, maybe -10s to +10s. It's completely up to you. You can always go back and change them if you want to, but you gotta start somewhere. Maybe we'll do 10s. Okay, so with the equation in and the window set, go ahead and hit graph. Alright, and let's try to figure out of these different combinations which one do we have showing up. So on this negative side over here, it looks like we cross 1 and then 2 times. Okay, we have 2 x-intercepts. So we know it's either going to be this option or this option, because those are the ones we listed the number 2 in. Alright, on the right hand side, it looks like we only touch once, okay? But take a look at that multiplicity. If you're just touching and bouncing, what's the multiplicity of that x-intercept? Yeah, 2. Okay, so even though you're touching even though you're touching once, it's actually counting as twice, because that's what the multiplicity is. So we have 2 on the left, but also 2 on the right. So out of the two possibilities we have here, it looks like this is the actual one for this graph. So we found the 4 possible ones, but notice how with a graphing calculator we can determine which one it actually is. Okay? We doing okay so far? All right, we're going to keep trying examples like that. Okay, so let's go ahead and try maybe the one on the next page. All right, so we're going to determine how many positive we have, how many negative we have, how many are at the origin, how many are imaginary. We're going to create that chart of possibilities or combinations, and then we're going to check it on the calculator. I know some of you might be tempted to go immediately here just to know what it is, but I want to see the work. Okay, I want to see the chart. I want to see that you understand kind of the process. Okay, so immediately looking at this equation, can we write down how many total x-intercepts we should be anticipating? Yeah, 5. Good. Okay, so let's maybe first start with the positive ones. How many are going to show up on the right-hand side of the x-axis? We're going to use Descartes' rule of signs. So take a look at the original equation and count how many sign changes you have. Good, Marie? We got 3. Let's see. I think we have 1 between the first 2 terms, then the next 2, and then the next 2. Actually, we change every single time. So the maximum amount we could have is 3 on the right-hand side. Or, what are some other possibilities? Yeah? Not 0. Yeah? 1. You subtract 2 every time. Now, if we subtract 2 from 1, we're going to have a negative number, but that's not going to make sense because you can't have a negative amount of x-intercepts. So these are the different possibilities for x-intercepts on the right-hand side. Let's go ahead and check out the negative side. So we're going to have to plug in negative x and see what that equation is going to look like in terms of your sign changes. So we said a little shortcut to help us here is all of the odd-powered terms are going to switch sign. So we would end up with a positive x to the 5th and then a positive 3x cubed. How many sign changes do we have in that new equation? Yeah? None. All right, so 0. All right, let's go ahead and list how many x-intercepts we might have at the origin, aka 0. What do you think? Yeah. Okay, so you can factor out an x squared. So we'll say x squared is a GCF. So therefore, how many do you have there? How many meaning multiplicity? 2. Okay, good. All right, now let's think about imaginary. You said we have a total of 5, but we can only have an even amount of x-intercepts. So what are some even numbers that are less than 5? Because we can't go above 5. 2, 4, maybe you don't have any. None are imaginary. Okay, so we'll do 0. All right, so with all these possibilities listed, we're going to create our combination chart, and once we have that chart, we're going to use the calculator to test to see which one of those combinations is the correct one. All right, so if we look at our different possibilities, maybe we have 3 positive x-intercepts. We'll never have any negative. We will always have 2 at the origin. So what does that leave for the imaginary option? 0, I heard it. Okay. Another possibility would be if we had one positive. We're never going to have any negative. We're always going to have 2 at the origin. So what does that leave for the imaginary? Yeah. 2. Okay. Are there any other combinations? I don't think so. I mean, I know we listed 4 here as a possibility for imaginary, but notice how if we did put a 4 here, there's no way that would work because 0 always is 2, right? And that would give us a 6, which is too much. So I think that's as far as we can go. So in this one, we only have 2 possibilities, not a lot, but we're going to check to see which one of those 2 is the correct one. So go ahead on your calculator and go to y equals, clear out the last one we did, and we're going to type in our new one. Alright, that might be a little hard to tell. Notice how we have a lot of extra space on the left hand side and the right hand side. So maybe we'll zoom in a little bit on this window. Instead of going from -10 to +10 on the x-axis, maybe we'll do like -3 to +3. And we can change the y's to those numbers as well. We'll kind of go closer in on the origin. Yeah. You both got error? Can you check and see how you typed it in?
That's what I was thinking.
Alright, that looks a little bit better for us to determine this one. So it looks like we bounce at the origin, okay, multiplicity of 2, and we cross once on the positive side of the x-axis. So looking at our 2 combinations, that would be the last one. We'll just put a little star there to denote that that's the correct combo. Not sure if you guys want to actually draw the graph. If you go back and look at your notes, like to help you study or help you with the homework, might not be a bad idea. We'll draw what this graph looks like. Something like that. You ready for another one? Give it a shot. Alright, let's go ahead and list our possible number of positive x-intercepts. Look at the sign changes. How many do you have? Yeah? Alright, so maximum amount of 3, but what's another possibility? Yeah? 1. Good. Alright. Let's go ahead and figure out the negatives. So we're going to have to write down that negative equation. If you were to plug in negative x for all the terms, only the odd powered ones would change. Alright, so how many sign changes in that new equation? Yeah? Just 1. We have it at the end, okay? We cannot subtract 2 from that because we would end up being negative, so that's as far as we can go. How about any x-intercepts at the origin? Do we have an x as a GCF? No. Notice how we have that constant term on the end, aka there's no x there, so there's no way we can factor 1 out. So we don't have any at the origin. All right, let's think about imaginary ones. What's our degree? Good, Marie? 4. Okay, so that's actually our total. Maybe we'll jot that down too. We know we should have it 4 all the time. 4 is an even number, so that's a possible amount for imaginary. 2 is also less than 4, so that's another possible one. And maybe we don't have any. Okay, so we're going to go ahead and create a table to check out all the different combinations, and then we'll check to see which one is correct. All right, so possibilities. We could have 3 positive x-intercepts. We'll always have 1 negative. We will never have any at the origin. So what does that leave as a possibility for imaginary? We got 0, right, because our total was 4. Another possible combination, we could have 1 positive x-intercept. We'll always have 1 negative. We'll never have any at the origin. So that leaves a total of 2 as the imaginary. I think those are the only 2 combinations we have. All right, so calculator time. Let's go ahead and check to see which one is the right one. We'll type in the equation. All right, looks like we have 1 negative x-intercept and 1 positive x-intercept. So based off of our chart, looks like the second possibility that we listed. Again, if you want to draw a little graph, you can. We doing okay? Hanging in there? All right, we're going to stop there for today. We'll save the other 3 for kind of practice and extra work tomorrow. And then we're going to take a look at some imaginary ones just a little bit further. Okay? I didn't mean tomorrow, I meant Monday.